Covalent bonds can be defined as purely covalent or polar covalent. Purely covalent is when, for example, in the case of diatomic hydrogen, the electrons are shared equally between the two atoms. A polar covalent bond is when the electrons reside closer to one atom or another. As in the case for hydrogen chloride, we would envision that because chlorine is has a higher electron affinity, the electrons will reside more towards the chlorine. So in this case, they're not equally shared, so we say that they are polar covalent. It's a polar covalent bond. The symbol with a partial symbol and a plus and a partial negative indicates that the electrons reside more towards the chlorine atom than the hydrogen atom. So this is the symbol that's used to show that the electrons are not equally shared. There's also a vector is used and pointing in the direction of the atom in which the electrons tend to reside. So in this way, we now have a pure covalent bond where the electrons are equally shared and there's no partial charge on either atom, or a polar covalent bond, polar being two poles, a positive pole and a negative pole. Now, it's important to note that there are different degrees of polarity, and so the electronegativity scale was developed by Linus Pauling and others to help quantify how polar a covalent bond is. As it turns out, the electronegativity scale is based on both the ionization energy and the electron affinity for the atom. And what we see is that in the upper right-hand part of the periodic table, the atoms are more electronegative, and in the lower left-hand corner, they are less electronegative. So that means that the atoms in this region of the periodic table have a stronger attraction when bound covalently to another atom. So electronegativity is the attraction for a pair of electrons in a covalent bond. So we use electronegativity to understand the attraction of the electrons in a covalent bond. A greater value for electronegativity means that it has a greater attraction. Now, to quantify how polar a bond is, the electronegativity values have been assigned. So this periodic table shows the electronegativity values. Note there are no values for the noble gases because noble gases don't tend to form covalent bonds, and they don't have electron affinities or ionization energies that make any sense in this context. So we just look at the elements that tend to form bonds, whether they be ionic or covalent. And the degree of polarity has to do with the difference in the electronegativity values between the two atoms found in the particular compound. For example, hydrogen chloride. The electronegativity value for chlorine is 3.0. Electronegativity value for hydrogen is 2.1. So for hydrogen chloride, the difference in the electronegativity values would be 3.0 minus 2.1 equals 0.9. Whereas for the hydrogen, the difference in electronegativity value is 0 because the values are the same. So hydrogen chloride would be considered a polar covalent bond. Hydrogen, diatomic molecular hydrogen, would be considered a nonpolar bond. Now, typically, if the difference in the electronegativity values is greater than 1.5, then one considers that bond an ionic bond. For example, if you look at calcium, calcium has electronegativity value of 1, and oxygen has electronegativity value of 3.5. So the difference in electronegativity for calcium oxide is 2.5. So anytime the difference in electronegativity is greater than 1.5, it's safe to consider that particular bond an ionic bond. Further, even though, let's take for example the bond between carbon and hydrogen. The electronegativity difference between a carbon-hydrogen is only 0.4. So we'd say that bond is nonpolar or very, very slightly polar compared to the HCl bond, which was a difference of 0.9. So we have a way to compare the differences in polarity of bonds, some bonds being more polar than others, based on the difference in the electronegativity values of those bonds.